Now, perfect. All right, welcome everyone. So I'm so glad you joined me. Thank you for taking the time out of, I'm sure, everyone's busy day, especially at lunchtime, to join us here today. My name is Terracina. I'm the project manager with the Chesapeake Water Watch here. And if anyone's familiar with the Chesapeake Water Watch, you know a lot of the work that we do is with satellites. The data we collect on the ground helps to validate and improve remote sensing satellites. And so that's a huge part of our project. And I realized, and I think the whole team realized, that there's a lot we don't know about satellites, or at least the general public. I'm including myself in that. And so this would be a perfect opportunity to run almost like a remote sensing 101 class. So today, that is all you're going to hear from me. We're going to pass it over to Britany in just a second, but some housekeeping things. So this is a mic off webinar for now. We will have an opportunity towards the end for you to raise your hand, and then I can give you some mic permission so you can ask questions. But in the meantime, you should have access to chat. Feel free to put any questions, comments, or introductions in the chat if you'd like. Please, if you are using the chat function and when you speak towards the end, keep it respectful. We have learning. This is a space of learning and curiosity. So please keep everything friendly, respectful, and curious. All right, Britany, am I missing anything?
No, I don't think so.
Wonderful. All right, in that case, I am going to go ahead and mute myself and pass it over to Britany.
All right, excellent. Let me just share my screen. Let's see. Let's make sure you should probably just see my background at first, and then hopefully the first slide soon. Do you see the first slide?
We see ya. They look great.
Okay, great. Also, I should just address this right away. My slides are in front of me directly. The chat and the Zoom call is on the second screen to my side here, so I'm not multitasking. I just want to make sure I can capture everything at once. But you do have my complete and undivided attention. But I should obviously start by introducing myself. Hi, everyone. Thank you so much for attending today's Lunch and Learn. I'm Britany Beaudry. I'm a member of the Giorgio Biooptics Lab at the City College of New York. And today we will be discussing the fundamentals of remote sensing and how this relates to Chesapeake Water Watch. This image we're looking at here was actually taken from the International Space Station, and it shows the Chesapeake Bay. And I think that it is quite a beautiful sight. So with all of that being said, let's get started. So here's a quick outline of what we will be discussing today. Defining remote sensing, its history, its uses, and a deeper focus on aquatic remote sensing in particular. We'll then discuss the role of in situ data and finish with some time for questions. If you do have any questions during the presentation, please feel free to write them in the chat and I will address them. But let's get started with what is remote sensing. I would love to begin by seeing what we all currently think at this time. Please feel free to write in the chat what exactly comes to your mind when you hear the phrase remote sensing. No pressure. It can be as simple or as complicated. You don't have to know the right answer. Maybe there isn't an exactly right answer, right? Satellite. Okay, great. Yeah. Satellite signals, information. I'm loving this. Yeah, excellent. Spies. All right. Yeah, observation. Okay, excellent. Well, remote sensing, as the phrase sort of describes, means that we are seeing something remotely or observing something from a distance. So within Earth science in particular, this specifically means using satellites and sensors that orbit our planet. This right here is a really nice animation of Earth and several of the satellites that currently orbit it. Each of these satellites carry sensors on board that were designed for specific uses related to monitoring our planet. But how specifically do these sensors monitor our planet? Well, satellites monitor Earth through the electromagnetic spectrum. capturing reflected or emitted energy across several wavelengths. This slide illustrates the electromagnetic spectrum, which includes all forms of electromagnetic radiation arranged by frequency and by wavelength. So on the far left of this image, we begin with radio waves, which have the lowest frequencies and the longest wavelengths. These waves are commonly used for radio, cell phones, and things like Wi-Fi. And as we move to the right, the wavelength shortens and the frequency increases. So next are microwaves, which are used for both household appliances, but also used in radar systems, including some used in ocean surface monitoring, as a nice example. As we continue further to the right, we reach the infrared region, where radiation is emitted by heat, like the heat radiating from our own bodies. And some satellite sensors also use infrared to detect sea surface temperatures and atmospheric moisture. And here at the center of the spectrum is the visible light region. This is the narrow band that our eyes can detect. So where we focus much of our ocean color remote sensing is within the visible spectrum as well. Satellites like Sentinel-3, Aqua, and VIIRS detect sunlight that has reflected off the ocean surface. And by analyzing specific visible wavelengths, particularly blue, green, and red bands, scientists can measurements of chlorophyll A, phytoplankton concentrations, colors, of organic matter, suspended sediments, and more. This makes visible light crucial for studying water quality and algal blooms and all the different biogeochemical dynamics in marine and coastal systems. You might notice that there's also the label here, a little to the left of the visible light, that says optical window. And that's because Earth's atmosphere allows most visible light to pass through without interference, which makes it ideal for remote sensing from space. And as we move to the even shorter wavelengths, we encounter ultraviolet, also known as UV radiation, which can cause sunburn. And then we move further towards X-rays used in medical imaging, and then finally gamma rays, which have the highest energy and are produced by things like nuclear and cosmic events. And these higher energy waves don't pass through the Earth's atmosphere easily, so we rely on space-based satellites to detect them. And then that's just a nice description. So at this point, you might be wondering what makes all these different satellites different from one another. And that comes down to the wide variety and the different kinds of resolution available within a sensor's design. Sensors on board Earth-observing satellites can have variations in spatial resolution, which is how large each pixel is in a satellite image, like in the figure in the top left. And sensors can also vary in temporal resolution or how often a satellite covers a specific area on Earth, like the figure in the top right. The orbit of a satellite determines its revisit time, and some orbits provide coverage every couple of days, while others can be just minutes apart. And there's also radiometric resolution, which is a sensor's ability to distinguish very small differences in energy or the reflectance. And this means it describes how finely a sensor can measure variations in brightness. So the higher the number of bits, the greater the sensitivity to these small changes in the signal. And you can see that represented in the bottom left figure there. And lastly, there's also spectral resolution. Spectral resolution is how finely a satellite sensor can distinguish between different wavelengths of light. That means how many and how narrow the band of the electromagnetic spectrum the sensor can sort of see. In the figure on the bottom right, you can see the differences between having fewer wide bands to having several smaller bands. So to go over some of these satellite variations a bit more, I'll start with spatial resolution. This image shows how much spatial resolution can vary between sensors and what that might look like within an image from a satellite. So on the left, a low resolution image has a larger pixel size. So within each pixel, things are averaged on a larger basis. And as we look at the images further and further to the right, the sizes of the individual pixels are decreasing, and this becomes a higher resolution image, which allows us to see more distinct features in variety. The spatial resolution of a sensor depends on the sensor design, the wavelength, and especially the satellite's orbit height. Satellites in lower orbits like Landsat can capture fine details down to about 30 meters, and then even less in some cases. Meanwhile, higher orbit satellites like MODIS provide coarser resolution, sometimes 250 to 1,000 meters per pixel, but because of their higher orbit, they can cover much larger areas more frequently. So there's a trade-off between detail and coverage based on the satellite's orbit, which helps determine its mission goals. And this slide is a nice example of spectral resolution and how it changes between various ocean color sensors. So on the left, this figure compares the spectral coverage of current satellite missions like MODIS, VIIRS, and ULCHI on Sentinel-3 with newer and future satellite missions like PACE, GLIMMER, and SBG. So the available bands and the width of the bands are represented vertically in orange across the electromagnetic spectrum. And you'll notice the older missions use fewer and broader bands, and these are known as multispectral bands. And these are sufficient for detecting sort of general ocean color features like chlorophyll A, but they can miss more subtle differences across the electromagnetic spectrum. So in contrast, the newer sensors like PACE's Ocean Color Instrument, OCI, offer hyperspectral resolution, meaning that they take measurements in hundreds of these narrow contiguous bands, with something like PACE sampling every 2.5 nanometers across the visible spectrum. And this greatly improves our ability to detect specific water constituents. And in the figure in the right side of the graph, or on the slide, you can see why this is so important to us. So the upper right graph shows what VIIRS sees, this multispectral instrument, only a handful of broad bands, so we only have a handful of measurements. And we can see that you can use it to distinguish between non-harmful algal blooms in black versus a harmful one in the red dots. But the resolution is coarse and we lose a lot of that spectral detail. And now looking at the PACE graph below it, with such a dense sampling across the visible spectrum, PACE can capture the full absorption curves of each bloom type, and it's much easier to distinguish between the harmful and the non-harmful algal bloom. And then this slide shows the history and continuity of the Landsat satellite program, which is one of the more important features of this timeline, is the idea of long mission lifespans and overlapping coverage. So this is important because environmental change, things like land use, coastal development, urbanization, water quality trends, and lots more, they can take place over decades. And without consistent long-term observations, we'd lose the ability to track these changes accurately. And while there are new and exciting satellites and sensors that would enable us to learn more about our planet than we ever could previously, it's also important to realize how much we rely on previous data from older satellite missions and how important it is that they continue to have this continuity and work together on future work. So when using satellite data to observe the environment, there are a lot of important factors to consider. The right choice depends on your project goals and the kind of information that you need. So for example, one satellite might offer better spatial resolution, but another might provide more frequent overpasses, making it better for capturing rapid changes. Similarly, a newer satellite might have cutting edge capabilities, but only a very short record of data, while your study may require decades of historical coverage, depending on what you're trying to understand. So because no single satellite offers everything, researchers often take a multi-sensor approach, which is combining data from different missions to fill in gaps and extend insight from across time and space. So the video here on the right demonstrates this in action. Landsat 8 and Sentinel-2 are frequently used together to complement each other's observations, providing a more complete and consistent view of the Earth's surface as they alternate their orbital passes. All right, so now that we have a nice understanding of what remote sensing is and how it works, I want to give a brief history of satellites with a special focus on aquatic remote sensing. So it all began in 1957 when the Soviet Union launched Sputnik 1, the world's first artificial satellite, and this kicked off the space age. And by 1972, we saw the launch of Landsat 1, which was the first satellite designed specifically for civilian Earth observation, paving the way for decades of environmental monitoring. In 1978, CSAT became the first satellite dedicated to ocean observation, showing that space-based monitoring could go beyond land. And through the 1980s and the 90s, Earth observation expanded with missions like NOAA's Advanced Very High Resolution Radiometer, AVHRR, giving us global weather and environmental data. And at this point, you might start to notice here how much we love our acronyms. Don't worry, there's plenty of more to come. But a major leap for ocean science came in 1997 with the launch of CWIPS, the first satellite focused entirely on global ocean color, which has been vital for studying phytoplankton and marine ecosystems. And then in 1999, MODIS was launched aboard both the Terra and the Aqua satellites, offering high-frequency, wide coverage observations across land, ocean, and our atmosphere. In the 2010s to today, we've entered an era of high-resolution multi-sensor systems with missions like PACE, the Sentinel series of the European Space Agency, and continued Landsat missions building on their legacy. Looking ahead, we're seeing new missions like NISAR, Glimmer, and even commercial small sats, also known as CubeSats, have started becoming used a lot by industry and within private organizations. So this right here is a really nice visualization of NASA's Earth observing fleet, starting in 2000 up to future missions in the 2030s that are planned. So these satellites each have their own mission goals and can be related to anything like observing changes in the atmosphere, monitoring wildfires, ocean color, the coverage of ice, and even more. So together, this fleet forms the backbone of global Earth observation, providing the data that researchers, policymakers, and communities rely on for various decisions and goals. But at this point, I'm getting a little ahead of myself. So the next question we're going to explore is, what can remote sensing be used for? But before we discuss this question on the next couple of slides, I'd like to know what you all think beforehand. What is something you'd like to see satellites used for? Please write your answer in the chat. Earth observing satellites have numerous applications, and you might be surprised to learn that there is a mission or a sensor already out there that can observe what you're specifically interested in. So, fingers crossed. Can't wait to see what your responses are. I'm seeing some more of the previous responses. Monitoring changes in species. All right, forests. Yeah. I'm working on some some missions back there. I think these are applicable. Okay, cool. All right. Finding abandoned oil wells. Okay, very interesting. World peace. That's very nice. All right. Feel free to keep, tsunami detection. Feel free to keep writing and we'll jump in to some of the answers. I don't have all of them. But in the top left, we can see here how satellites track land use and land cover changes, which are essential for managing development, deforestation, and conservation. Another example on the top right, they help assess agricultural health, monitoring crop conditions, and productivity over time. Satellites also play a critical role in air quality and human health, shown here with maps of dust transport over South Asia, which affect respiratory health and the climate. And in the bottom left, we see disaster monitoring, such as this image, which is from a wildfire in California last year. Satellites provide rapid response data for events like fires, floods, and oil spills. And finally, they're also essential for tracking climate change and weather patterns, with this view of Hurricane Dorian from EcoStress, which captured land surface temperatures and storm dynamics. So there are many, many more applications on Earth with Earth observing satellites towards the needs and the interests of society and our environment. This is just a glimpse into the possibilities of remote sensing and its different opportunities. But here at Chesapeake Water Watch, our focus is on aquatic remote sensing. So while Earth observing satellites have many applications, we place special emphasis on how they're used to monitor aquatic systems. Using satellite imagery, we can detect both long-term environmental changes and short-lived episodic events in water bodies. This includes tracking water quality, detecting harmful algal blooms, mapping floating algae like sargassum, and monitoring oil spills and coastal habitats. These aquatic observations are deeply connected to many aspects of our daily lives. They influence surface currents, fisheries, food security, navigation, and our ability to respond to floods and storms. So satellites can even help detect pathogens, support recreational use, guide tourism, and improve forecasting efforts. In short, water seems to connect everything, and satellite data allows us to better understand, better monitor, and better protect this vital resource on a global scale. So let's jump into a little more of the technical background of how aquatic remote sensing works and what exactly we are measuring when we use these sensors. Okay, so this video here highlights how a satellite such as Landsat 8 is able to capture changes in water quality conditions. Landsat 8 works by measuring that amount of sunlight that was just reflected back from Earth's surface across multiple wavelengths. And by analyzing these reflectance values, especially in something like the visible or the near infrared region, scientists can detect key water quality parameters and even distinguish between types of algae in lakes, rivers, and coastal waters all around the world. I again just want to highlight how this satellite is specifically monitoring the reflectance back from Earth. After the sun hits the planet, this reflectance back to the satellite is what we are capturing with the measurements and what we are working with. So this image shows a true color Landsat 8 view of the Wicomico River and the Chesapeake Bay taken in October 2014. What you're seeing isn't just beautiful, it's telling us a lot about what's happening in the water based on its color. So on the left here, we have 4 sample spectra of water leaving radiance. That is sunlight reflected from the water surface that reaches the satellite across various wavelengths. So each curve corresponds to a different water quality condition. Starting at the top here, sediment-rich water reflects a lot of light across the visible spectrum, and you can see it peak in that green-yellow range of wavelengths. And that's what we see in the upper part of the river, this light green water full of suspended particles. Next is CDOM, dominated water, which stands for color dissolved organic matter. This absorbs very strongly in the blue and the green light, and when it reflects, it gives a nice dark sort of browner look. Next is phytoplankton, which shows strong absorption in the blue and the red, and a really high reflectance in green, which is the greenish hue, which you kind of see in that zone where it's highlighted in the yellow box. And finally, clear water reflects less overall, particularly in the blue-green range, giving it that deep blue tone that we see further out into the bay. By analyzing reflected light across all these different wavelengths, we can begin to understand water quality, biological activity, and sediment transport patterns, all from space. All right, so this slide shows how we use satellite observations of water's color to estimate important biogeochemical properties in aquatic systems. So starting with this diagram here on the right, we see a conceptual overview of the different components that influence water reflectance, which is again what that satellite is seeing from the water surface. So this includes phytoplankton, color-dissolved organic matter, and suspended particulate matter. Each of these has unique optical properties, specifically how they absorb and how they scatter that light in the water. So these interactions shape that spectral signature that you saw in the previous slide in what reaches the satellite sensor. So these optical signals can then be linked to broader ecological processes like primary production, carbon cycling, and water quality, but doing that accurately depends on solid modeling, which brings us to this image here on the left. So here we start with remote sensing reflectance, which you might see as a RRS, measured at different wavelengths. That's 412, 443 nanometers. This is across the electromagnetic spectrum. And these values describe how much light is leaving the water at each wavelength, and it's again shaped by that what's in the water. So through this process called inverse modeling, we work backwards through these measured reflectance values to estimate inherent optical properties, also known as IOPs, or biogeochemical concentrations like chlorophyll A, CDOM, and SPM. So inverse modeling essentially lets us infer the cause, the materials in the water, based on the effect, which is how light behaves at that surface. So in the center of the panel here, we have an output map of estimated chlorophyll A concentrations derived from applying these models to reflectance data. And this process, excuse me, sorry, this process transforms satellite imagery into meaningful quantitative insight about aquatic ecosystems, but only if we have confidence in the models that we use. Just need water, give me a sec, sorry. Whew, sorry about that. So again, this central map is estimated chlorophyll A concentration derived from all of this information from this reflected data. And this it only works if we are confident about the models that we're using. And that brings us to this critical point. All of this remote sensing analysis depends heavily on accurate in situ data. So ground truth measurements are essential for developing and validating these models, ensuring that what we're seeing from space reflects what's actually happening in the water. So in the next and final section, we will look at the role of in situ observations and why they're still such a vital piece of the remote sensing puzzle. And here's some really nice images of some of our volunteers here at Chesapeake Water Watch. Sorry, I just need a little bit more water.
And really quick while you're grabbing that throat relief, hopefully. Just to define in situ or in situ means kind of like in the field, so on the ground data. That's what we're collecting with Chesapeake Water Watch. I know sometimes, we use some technical language and forget that I don't know if I learned in situ until a few years ago. So I want to throw that in.
Yeah, thank you very much, Roy. All right, so this slide shows how full ground truthing process from data collection to algorithm refinement. The in situ data is absolutely essential for both calibration, that is tuning the algorithm, and validation, which tests how accurate it is. Here, volunteers collect water samples and light reflectance using the Hydrocolor app, and these observations are uploaded to FieldScope, a shared database. Scientists then validate these samples in the lab and use them to adjust remote sensing algorithms. The end result is a more accurate satellite product tailored to local water conditions because the algorithm is grounded in real-world measurements by our volunteers. This is how we turn raw satellite imagery into reliable, high-resolution water quality maps. Here, we highlight how our volunteers' data fill critical spatial and temporal gaps. So on the left, you can see traditional water quality monitoring stations used from the 1980s through 2021. They're excellent for long-term trends, but they are somewhat limited in their spatial reach. On the right here, we see Chesapeake Water Watch volunteers and where they've sampled between 2021 and 2024. They dramatically expand our coverage, especially in nearshore and vulnerable communities, which are often the hardest to monitor by satellite alone. In the lower panel, you can see time series data for color-dissolved organic matter collected by their volunteers. And these consistent matchups with satellite overpasses allow us to fine-tune our algorithms and track real-time dynamics in local water bodies. And finally, in situ data helps us interpret what the satellite is seeing and even catch events we might otherwise miss. This series of maps shows turbidity, chlorophyll A, and color-dissolved organic matter across several tributaries in the Chesapeake Bay. And the colored dots within these are in situ measurements that were taken within the satellite's observation window during its overpass. So these anchor the satellite maps to real-time observations, making sure that the color gradients reflect actual conditions on the ground and are accurate. So this is especially important for tidal tributaries and estuaries where water conditions change quickly. And in situ data helps detect and diagnose key events like algal blooms, runoff after storms, and sudden shifts in water clarity, providing context for what the satellite alone might not fully explain. So that was all the informational slides that I have prepared for you all. So as we start to wrap things up, I'd love if you could answer this question in the chat. What is something new or even just something interesting that you learned from this webinar today? I'll give you a little bit of time for that. And of course, while you're writing that, here's a quick overview, not trying to influence your answers, just providing a quick overview to summarize some of the main points. Satellites have sensors on board that can detect reflected or emitted electromagnetic energy across different wavelengths. These different sensors come with a lot of variability in regards to spatial, temporal, spectral, and radiometric resolution, and have strengths and weaknesses depending on your field of interest. Collected in situ data is very essential for determining the accuracy of satellite algorithms and improving the monitoring capabilities of satellites and their various parameters. And in aquatic remote sensing, we are able to use these parameters to support critical ecosystem changes from local to global scales. And lastly, I have listed some initial resources related to our work, our lab here at CCNY, the Chesapeake Water Watch's most recent publication about aquatic remote sensing, and some additional trainings about remote sensing and satellite applications from NASA's RSET program. I also included a link to NASA's Earth web page, which features information on current and future Earth missions that you may find interesting. With all of that, that's all I have for you today. Are there any questions at this time? I don't know if people want to raise their hand or if there's anything in the chat that I could address. I can either stop sharing or I can keep sharing my screen to show specific slides if there's anything people want to learn more about. Happy to.
We had a question a little while back
Mhm.
from Tom, I believe. What are water quality standards being EMT and why not? That makes sense? That was back at 12:23 p.m. today. No, that makes.
12.
Hey, it's Tom.
Oh, Tom. Yeah. Thanks.
Yeah.
Sorry, that's a typo. That's Met.
Ow.
Just
Oh,
immediately look for the acronym. No, just use of these things and determining whether regulatory water quality standards are being met and detecting problems from there, or causes of
Yeah.
problems.
Yeah. Satellite remote sensing, aquatic remote sensing is very relevant to this. Yeah, it can certainly look at different water quality standards, whether or not they're met on local and regional scales. I would think local scales, you would want a satellite that has a smaller spatial resolution so you can monitor that more clearly. But yeah, you can look at concentrations of things like chlorophyll A, organic matter. You can even look at pathogens, something like harmful algal blooms and sediment from runoff from the land after a rain event, and you can look at the sort of discharge from a river, and that can help you understand whether there's runoff and how that's affecting the water quality in the nearshore environment. Does that help answer your question?
Yes, I'm sorry. Thank you.
Okay. Yeah, no, sure thing. All right.
All right. Another question in the chat. I'm trying to get in kind of sequential order here. By Ted and Janet, how much impact does cloud coverage have?
Oh, excellent question. Yeah, cloud coverage has a huge impact on ocean color remote sensing because, as I said before, maybe I can show a nice slide rather than just the resources page. This is a great example. So we're talking about these atmospheric windows with the visible light. That's where a lot of ocean color is coming through. But clouds are blocking that from occurring from going back from Earth to the satellite itself. Clouds interfere a lot with satellite imagery. There are other types of satellite imagery that use radar that maybe are able to work around clouds, but for ocean color in particular, clouds have a huge impact. And when we work with satellite imagery, sometimes we'll just mask out the clouds. You might hear that phrase sometimes where we remove the clouds from the imagery, and then we might have these gaps. And there's some people who try and specialize in filling those gaps with interpolated data and whatnot. But you can only work with, where there isn't clouds when you're working with an overpass initially.
Selfishly, I want to throw out there for Chesapeake Water Watch, even if we have collection events on days with lots of clouds, even though the satellites may not be getting the imagery that we'd like them to get, it is nice to also establish trend lines with the data in general. So not to discourage anyone.
Right.
We still need your
Yes,
samples
yeah.
on cloudy days.
Yes, we do. Yeah, it is important to understand. And, clouds can sometimes bring things like precipitation events, and understanding what's happening in the water during that is very important as well.
All right. So I think Mrs. Conrad has a question. How much of the EM spectrum can't be viewed through the atmosphere?
Oh, I think we're on the perfect slide for that. So you can see these atmospheric windows where we're able to penetrate the atmosphere and see a couple different wavelengths. That's where a lot of our satellites are. But again, in these like higher areas, this atmosphere, it says opaque to wavelengths. So these wavelengths can't really penetrate the atmosphere. So it doesn't make sense to have a satellite looking at Earth when it can't really get through. So we have a lot of higher wavelength satellites in space looking at different sort of far away astronomy-based information. But yeah, for the most part, for Earth observing satellites, we're looking at like radio, some microwave, and a huge portion is the visible spectrum.
Let's see. I understand this can be sample collection as well as spectrometry. Oh my gosh, I'm startling here. Spectrometry station, right? Says our king.
This can be sample collection. Yeah, I think I understand what they're asking. Maybe this is a good example. So here, on the left, there's this traditional water quality monitoring stations, and those red. Those can have like USGS, sometimes they have like spectral, like long-term sampling at those sites. And then sampling in the blue from our volunteers using like water samples. Are you saying like, are you able to sample both spectrally and with the water quality itself? The answer to that would be yes. You can use different spectrometers and whatnot out at sea, along the coast, in the water, as well as the quality of like chlorophyll and sediment and whatnot.
And Arking, if we did not answer your question, feel free to pop
Yeah,
on.
yeah. To let us know if I can clarify anything there.
Yeah, my name is Russ. I should probably clarify that, but no, you did. That was fine. Thank you.
All right, let's see here. You guys have so many wonderful questions.
Yeah,
And also
great. Thank
takeaways.
you.
These are very warm, fuzzy.
Oh,
All right, Angie Kim says how satellites collab to create images more effectively and or efficiently. So I'm assuming that's something that we learned, which is also very cool, right? That visual of the two satellites were really cool. Maybe met. Oh, were you trying to help us figure out the early
Yeah, I
question?
was gonna help with the typo.
You're awesome. Thank you.
appreciate it. I'm glad I can show you the visual again, at least.
Okay, let's see. Oh, Caroline, are there satellites just for water rising?
Yeah, there are, I think the word is altimetry satellites. Those measure the surface of the water, and you can look at things like changes in water level height over time. And that's used to look at things like, changing tides, and also sea level rise, which I think is what you might be asking. You can also look at, what's the word? Those large, like water reservoirs and the level of water in those. Yes, there are a lot of satellites out there that measure sea level rise and sea level height for a bunch of different applications. I think one that's really popular is the Jason. I think Jason 3 in particular is one that can do that.
All right, let's see. Oh, what are the spatial resolution of Landsat and Sentinel pixels?
Great question. So Landsat, for the most part, it's about 30-meter resolution. you can think of that as like a baseball diamond. And then for Sentinel there, so Landsat is continuous, where it's just this, it's sort of the same values over time. Sentinel varies a bit because there's differences in the bands and the measurements between Sentinel-2 and Sentinel-3. So there's a lot more variety between the Sentinel series. Sentinel-2 and Landsat, which I'm showing here, which work together a lot. They're about the same. Landsat, I think, is about 20-meter resolution. So that's 20 by 20 for each pixel, and they work together. Yeah.
All right. Ooh. Wow, Tom, I don't know if anyone has this answer. What will we be able to do in 2030 that we can't do now?
That is a great question. I think there's, satellites in their missions, they're improving every year, they're improving every day with all of the research and work that goes into them. I think with the launch of the hyperspectral instruments like PACE and like Glimmer, here I can pull up like a nice slide. This one, I think this is a really nice example. Again, with when you're looking at like MODIS, when you're looking at VIIRS, and even ULCI, you can see that these bands, they're pretty wide, they're multispectral, and with PACE and Glimmer and SBG, they're so narrow. When you look at the figures on the right, the information that you get from MODIS, VIIRS, and ULCI, there's just a few points for different sort of like swaths of the wavelength, these big chunks, these widths. Meanwhile, at PACE and these other hyperspectral instruments, you're getting measurements at very specific wavelengths, and you get this really nice, beautiful spectral signature that allows you to see so much more. So I think in terms of what we will be able to do in 2030 that we can't do now is I just think our level of understanding of very specific water quality indicators and the impacts that they have over time, and just our ability to improve our understanding and to detect them. And that even goes to different things like oil spills and sargassum, giant mats of algae floating out in the Caribbean Ocean. The Glimmer satellite as well, it's hyperspectral, but it's also geostationary. So instead of that previous visual that I showed you where they're a polar orbit where they're moving north to south, Glimmer rotates, it has an orbit at sort of the equator to move at the same period as the Earth rotates, so it's always over the same spot. It's the same as like a weather satellite. So we would be able to get measurements much more frequently, and that'll really improve our understanding of how these different water quality parameters change over time. Just having that data on a very, very small time scale compared to waiting for like days at a time for a new image. I think I could talk about this all day. But I hope that answered your question.
Tom says good answer, so I think he approves.
Great.
Also, it sounds like a very hopeful future. That's wonderful.
Yeah.
Let's see. Is there a way to know, this is from Josie. Is there a way to know what the signal is picking up without field or in situ observation?
Yes, I would say I say yes with like an asterisk. I would say yes now. There are things like Landsat that are out there that, I could, make a Landsat image of an area around here today and be pretty confident about what I'm seeing. But I'm only confident in what I'm seeing because of the huge history of the in situ data that has already existed for the satellites themselves. In situ data, ground truthing for satellites is just so essential to making sure that they're accurate and that they're calibrated on a local scale for very specific algorithms at your area, but also on a global scale. Right now, the PACE has the science validation team working all across the globe to get different water quality parameters, and they're doing very similar work to what the Chesapeake Water Watch team is doing on a local level, just getting these measurements to improve the satellite over time, and that happens with every mission that's occurring. So Great question, Josie. I would say yes, but it's still based off of the work that's already been done with in situ data.
She was paid to say that. Keep collecting data, or Chesapeake Water Watchers. Um, no, just kidding. All right, let's see. Geostationary satellites for ocean color. Woohoo! Said Maria.
Yes, they're
Coming
so
up.
yeah, it's something we don't currently have. It's so exciting for this part of the world. I'm very much looking forward to the launch of Glimmer. Stay tuned.
All right, and that seems to be the end for now of the chat questions. So if anyone has any other questions they want to verbalize, feel free to raise your hand and then pop on. See, I can't see one. There we go. All right. Well, while people are thinking of their questions, I'm going to go ahead and plug some, speaking of Chesapeake Water Watch, plug some upcoming things that we have going on. So many of us may already be involved with the Chesapeake Water Watch, but if you are not, we have the perfect opportunity for you to learn more about the project and also how we use Hydrocolor, one of the tools that is a free smartphone app. And then you have to buy a $10 piece of equipment, but we'll talk about that. If you'd like to learn more about that, we have a training coming up, I believe on May 6th. Oh, and we got another question from Jeff. Perfect. May 6th is the Tuesday. It should be from 5 to 6:30. We will be sending out links to register for that. So however you got the link for this, it should be on that channel as well. So look out for that if you're interested in getting involved. And this May, we do have a double overpass where our data collected goes a little bit farther. And that double overpass is going to be on a Saturday, May 24th. So if you are out and about right before Memorial Day and you're by the bay, the Chesapeake Bay specifically, feel free to take a few hydrocolor readings that would help us make these satellites even better. All right, we got one more question from Jeff. I believe it was Jeff. Yes. With 30-meter resolution, is there useful data from mixed water and land pixels?
Jeff, that's a great question. Yeah, there's this is usually referred to as the adjacency effect, where when you talk about the size of the pixels along the coast, part of this 30-meter, 250-meter, whatever spatial resolution, it could include part of the land and the ocean. So when we're looking at a single pixel and we're getting a value from it, we do have to think about, is this value coming from part of the land or just the water itself? For the most part, a lot of people will just try and not include a pixel right along the coast. But there's also people who are determined to sort of figure this out with spectral unmixing. I think there's a lab out in University of California. I don't remember which specific university. They do work like this, and they try and look at this with specifics to, I believe, seaweed and whatnot. But for the most part, the adjacency effect is a very big issue in at the front of the mind of everyone that uses satellite remote sensing. But yeah, I hope that answers your question, John.
Well, and then we have a housekeeping question. Tage in the chat is also a paid volunteer, paid actor here. Is there a place where you'll be able to access the recording for this webinar? I have a friend that likes this sort of stuff. Don't we all? I think at least we have one friend, right? Yes. So everyone here, and there's a bunch of other people who registered but did not make it. You guys will receive a link to this recording. The plan is to clean up, the front and the end portion, and then we're going to pop it on YouTube. And the hope is to share it on the Chesapeake Water Watch page. And I can pop the link here in our chat. But yeah, so we'll have it publicly available via the Chesapeake Water Watch page once we are able to upload it to YouTube, which shouldn't take longer than a week, I think.
Great.
We're on government time here. All right. Any last minute questions? We only have about 5 more minutes. If you are heading out to scarf down the rest of your lunch in these 5 minutes, Thank you so much for joining us. Britany, thank you so much for your time, your knowledge, and your wonderful answers to our questions.
Thank you, everyone.